Now, in terms of technological advancements, few things really have generated as much excitement, anticipation, and perhaps a little trepidation as generative AI. Now, the term itself refers to a type of artificial intelligence that can be used to generate realistic output such as text, images, and even video and music. Often this content can be generated by simple text prompts, so anybody that's familiar with ChatGPT or other similar systems will have an understanding of how these systems are actually able to understand quite sophisticated text prompts and are also capable of generating sophisticated output of their own. Now, generative AI really is driven by some key advancements in the field of AI in general. So things such as generative adversarial networks, which we'll talk about in more detail later in the course, and also developments such as natural language processing and large language models, techniques and models that have really driven these advancements in generative AI. Now, in terms of the evolution and the early development of generative AI, well, it can trace its roots back to, if we want to, all the way back to the early work in the 1940s and 1950s on AI and machine learning. But really, if we're talking about generative AI in particular, one of the really significant milestones was in the 1980s and the further development of more complex multi-layered neural networks. Now, in particular, the development of the backpropagation algorithm is significant since this is used in modern neural networks, and this is a foundational component of any generative AI system. Now, jumping forward slightly, we move to 2014, and really this is another key milestone because this marks the emergence of a concept known as generative adversarial networks. Now, we will talk about this in more detail later on, but ultimately these neural networks consist of a generator and a discriminator. A generator, its job is to produce content, and the discriminator, its role is to effectively judge whether this content is artificial, i.e. it's been created by the model, or it's genuine, it's real content. And it does this by utilizing machine learning to have an understanding of what real content looks like. And this was initially developed by Ian Goodfellow and colleagues at the University of Montreal in Canada. And really this is a foundational component of today's modern generative AI systems. Moving on then, there are other key developments. So there are two here from Google. So we have Google WaveNet in 2016, and this is a tool for text-to-voice synthesis, and it used neural networks to improve the quality of this synthesis. So what we're saying here is that this system was able to further enhance computer-generated voices so that they sound more human-like. Next, in 2018, we've got BERT, or bidirectional encoder representations for transformers. Now, this is used in machine translation contexts. And what BERT does is it utilizes machine learning to improve the quality of language translation. It does this by enabling a better understanding of nuance and context in language. Now, 2018 also marks the first release of the GPT, or Generative Pre-trained Transformer model from OpenAI, and this would lay the foundations for products such as ChatGPT, which I'm sure many of you will be familiar with. And then moving on to 2020, and really 2020 can be seen as the big bang in terms of bringing generative AI from the realms of research papers into public consciousness, into the mainstream. So this year marks the first public release of ChatGPT. And this was really the first chance for the general public to interact with these generative models. And with ChatGPT, we're able to interact using text-based prompts. The nature of GPT means that this language understanding is much more sophisticated than earlier systems. And also the output that it's capable of generating can be quite sophisticated as well. So it's able to use language much more naturally than previous systems. And we can use ChatGPT to generate text-based content for things such as blogs or emails or marketing, for example. It can be used to generate fictional stories, and it can even be used to generate programming code. Indeed, quite a significant use case now for generative AI systems such as ChatGPT is in the generation of programming code. Now, more recent developments allow ChatGPT to even produce particular file formats, for example. And this really is an area that is continuously developing and being refined and improving. So really that brings us up to the present day, and really the rate of change over the last few years from 2020 has been quite significant, and it will be interesting to see just how far generative AI develops in terms of the sophistication of its output. We've talked already about how generative AI is capable of producing quite sophisticated and realistic output. Now, the key to this lies in how the models are trained and the data sets that are actually used in this training process. Now, two foundational concepts are neural networks and the concept of deep learning. Neural networks are inspired by the structure of the human brain and how the human brain works to make connections and associations when learning new skills or learning new content, for example. So if we think about riding a bike, when we first start to ride a bike, the muscles that are required for that are not necessarily coordinated. So, we're a little bit unsteady at first. The more and more that we practice that, the stronger those connections grow in the brain, and the better we are able to ride the bicycle. Now, neural networks follow a very, very similar concept. So if you think in this example, if we're trying to train a simple classification model where the idea here is we have to be able to discern between pictures of dogs and pictures of wolves. So we're going to train the model up, first of all, using this neural network structure. So as we can see, this consists of a number of different layers. Different processes take place at each layer. So it may be that we take that initial training data, it's then broken down into simple shapes. And this is where we start to discern the different attributes that the model will see or detect in the image. So we also have hidden layers where more complex and abstract connections are made with the data. So we can see in this example then, we've got an input, which is an image that we're going to put into the model, and the model itself needs to use the training data to analyze whether this image is of a dog or of a wolf. So we can see here that it's able to do that by comparing what it's learnt through the process of understanding this training data. It's able to apply the different things that it's learned and the different categorization, the different connections that are made between these nodes, so between the layers, so we refer to these as neurons, and it's able to use that to calculate the probability that the image here is 90% dog and 10% wolf. Now, clearly there's going to be some commonalities between images of dogs and wolves, and the role really here is to train the model to be able to look for distinguishing features. And neural networks using what we call the back propagation algorithm, which we mentioned earlier, are generally used for these types of training tasks. One of the most important things when it comes to training models is to be able to evaluate their performance. And one of the ways that we can do this is through the use of a loss or cost function. And this is something that we'll talk about later on when we talk about generative adversarial networks. This is a key component in terms of how we can measure and refine the quality of output from these systems. But we can simply think of this as a scoring system. And the type of loss function that we can use will generally depend on the scenario. Two of the most common approaches are mean squared error and cross-entropy loss. Now, mean squared error is useful for regression problems. That's where we have continuous data rather than generating fixed values. So things such as weather predictions or financial modelling, for example. And what we do with mean squared error is we ultimately calculate the difference. We square the difference between the predicted and actual values, and we then work out an average from there. And this can obviously get quite complex, but all we need to bear in mind here, and we'll look at a visualization of this momentarily, is that we are simply comparing the difference between a prediction and the actual output. And by doing this, we get an idea of the accuracy of the model. Now, cross-entropy loss is a system that, again, we'll look at in more detail, but this is commonly used for classification problems. So a classification problem is very much like the example that we used earlier, where we're designing a model to distinguish between pictures of dogs and pictures of wolves. Now, typically the way that this works is that we're assigning a probability value between 0 and 1. So in the previous example, we actually used this as percentages. So we identified that the output, the image that had been input, was 90% dog and 10% wolf. So it was 90% likely to be a dog. Now, in this scenario, we're effectively measuring a range of values between 0 and 1. So when we input an image into the model, ultimately it's got to guess as to whether this, make an educated guess as to what the image contains. And its accuracy can be measured on a scale between 0 and 1. If the picture of a dog was inaccurately identified as 100% wolf, for example, well, this would have measured 0 as the value. If it identifies that it was 100% dog and this was correct, then we've got a value of 1. Now, the way that cross-entropy loss works is it will effectively penalise wilder guesses, if you will. So the further away the prediction is from the actual result, the more harshly the model is penalised. And this has the effect of allowing the model to quickly realise where it's going wrong and to take appropriate action to refine and improve the results of the output. So we can take a look then at a bit more detail at mean squared error. So we can see here on this graph we're plotting a range of different values and we can compare the actual value against the predicted value. And this gives us an idea of how far out the model is in terms of making its prediction. So quite straightforward in terms of concept. Now, we haven't added the squaring here, as the actual mathematical process isn't particularly important, but ultimately through mean squared error, we are trying to identify an average of all of the differences between predicted and actual values. And by doing this, we can measure the performance of the model. So obviously what we want to see is that the predicted value is much closer to the actual value. So the lower the mean squared error, the more accurate the model is and the more the predictions match the actual data. So looking at cross-entropy loss then, so we can visualize this using a graph. So if we think about our classification problem, we can use a simple classification problem. Is this image a dog or a wolf? And we can see that if we correctly identify with 100% certainty that the image is that of a dog, this would place us on the right of the scale and there would be no loss. There would be no penalty for that since it's 100% correct. But we can see this logarithmic scale is used to increase the penalty the further away the prediction is from the actual value. So if we were to input an image of a dog, and the model said that this was 0% dog, so 100% wolf, we would place this on the far left of the scale and it would be much more harshly penalised. So in this example, it would have the highest loss penalty. And of course, this is a really quite a quick way to improve the performance of a model, since the model learns that the further away the guess is, the wilder the guess, the more harshly it will be penalised. So it learns to refine its output more and more by going through this process until we've reduced this loss as much as we can. Another important consideration when it comes to the training process for generative AI and indeed other machine learning models is the data itself that is used as part of this training process. Now, generative AI models require vast data sets that consist of huge volumes of pre-existing data. And of course, size here is an important consideration. We need to ensure that we have sufficient volume of data to ensure that the model can be properly trained on a wide number of different attributes, scenarios, that the data set itself is sufficiently diverse, which we'll talk about in a moment. And the quality itself is also important. So we must ensure that the data is accurate that's being used in the training data, and that data is pre-cleaned, and that the data itself that is being used as part of the training process is appropriate. So moving on then to diversity and representation. We need to ensure that we cover a wide range of attributes, again, or demographics or scenarios in our data set to ensure that we have accurate and realistic results. So a good way to think about this is if we think about our earlier classification, our simple classification model, so identifying whether an image was a wolf or a dog. Well, in this scenario, we must ensure that we have a diverse range of images. So it's no good having 80% images of dogs and 20% images of wolves, because that's going to distort the results. So we need to ensure that we have a balance in our data set. we also need to ensure that the data set itself is representative. And this can have implications on systems that are used with humans, that are used in the decision-making process for things such as credit scoring, for example. Well, we need to ensure that no one particular demographic is disadvantaged and that they are proportionally represented in the data set, since this will have an impact on the output itself. And in some cases, we may even see amplification. So if there is a lack of diversity and representation, or indeed if there is some bias in the data set, this can potentially be amplified in the output. And certainly this is something that has been in many different news stories around the use of AI in scenarios such as law enforcement and credit scoring, for example. So this brings us nicely on to the next point about bias and ethics. So we will talk about bias in more detail later on. So when training up a data set, and we'll use the example of perhaps looking at some sort of system that can be used in employment. If we train this system and we don't include sufficient diversity in terms of different demographics, well, again, we may find that one particular group is underrepresented or not represented fairly. And of course, we have an ethical responsibility to ensure that no human is disadvantaged or unfairly represented because the data that we've used as part of the training process also wasn't sufficiently diverse. Next, we've got licensing and accessibility. Now, the use of generative AI has caused some consternation in terms of the lack of transparency as to which data has been used to train these models. So for GPT, for example, there are a number of organisations that are taking action against GPT on the basis that their data may have been used as part of the training. And it becomes a little bit of a grey area here, since we don't see the data that's being used as part of the output, it's simply used as part of the training process. And as we move forward, it may be that regulation or legislation is put in place that mandates the producers of these AI systems to ensure that data is properly licensed and also to ensure that there is transparency around the use of the data set. And then finally, we have data augmentation and synthetic data. So we can actually use artificial intelligence and machine learning to generate synthetic data that can be used as part of the training process. So this is almost in a loop, if you will. So we can generate synthetic data, we then put that back into the process as part of the training data, and we can also augment existing data. And this can be useful in scenarios where we have data protection legislation or we have sensitive data about individuals or organisations. Well, what we might take steps to obscure that data or to add additional data that needs to be taken out for privacy reasons. So this is where data augmentation can come into the process. But ultimately, this last point here is about the use of AI and machine learning to generate data that can itself be used to perhaps then train another machine learning model. So these are all incredibly important considerations, and we need to bear in mind once again that the quality of data used as part of the training process will have a direct impact on the accuracy, the quality, the plausibility of the output from a generative AI system.